Okay, be honest. How many of you guys jumped ahead to this episode because you saw the word password cracking? Okay, well, this is about password cracking, but more importantly, we're going to be addressing a lot of objectives that talk about, from a cryptographic standpoint, how a lot of attacks take place, and passwords are a great place to do this. So let's take a moment and start by talking about, where do passwords get stored on systems? Now, keep in mind, folks, when we're talking about passwords, we're talking about logon passwords in like a Linux or a Windows system, but we could also have, for example, on a wireless network, if you have a encrypted SSID, you have to have a passphrase with that. So the word password starts to morph fairly quickly into the term key, but we're going to talk about that in just a moment. So first of all, let's talk about storing a password. Let's pretend for a moment there's only one computer on the entire universe, and it's a Linux box. And if anybody wants to use this computer, they have to walk up to it and they got to log in, okay? Now, when they log in, well, first of all, someone has to create an account for it. And when that account's created, there is a place, and it's a little bit different on different distributions, but there's always a place where you have a list of all the usernames and then the password. But if you take a look at it, you see the password isn't in clear text, it's hashed. So it's going to look something like this. So we have, it almost kind of looks like a two-column spreadsheet. We have all these usernames, and then we have the hash of a password. Now this works out beautifully, because anytime anybody walks up, the moment you type in your username and you type in your password, my password is going to be Timmy, so I type in Timmy, and the moment I hit enter on that Linux box, the Linux system instantaneously hashes that password and then compares it to my list, and if it matches, then I'm authenticated and I'm on the system. So, and that's pretty much universal for how passwords are stored. It's invariably some kind of hash. Now there's a problem with that. And the problem, first of all, is that we have to deal with these things called people. So what we can do as people is we tend to use passwords that are fairly predictable. So if I want to crack that password, well, one of the things I can do is use what I call brute force. And by the way, folks, there are tons of software tools out there that are designed to help you with this. They have names like Offcrack and Cain and Abel. There's a ton of them out there. And what they'll do is they'll go, okay, here's where the password hashes are. I need you to attack it. And the software goes, okay, I can do that for you. How long are the passwords? So you got to give it a little information. And what will happen is, first of all, it can do a brute force where it'll sit there and go, okay, I'll do lowercase a, hash it. Did that match? No. Okay. Uppercase a, did that match? No. Okay. Lowercase a, did that match? No. You get the idea? So brute force can be, well, brutal in terms of the amount of time it can take, but it does absolutely work. The other nice thing about human beings is that we use human words for our passwords. I mean, it'd be nice if people could use terms like Anyuk7 or things like that as a password, which, by the way, is a search radar on an F-14 Tomcat. But anyway, the bottom line is that as an attacker, I know to just try to use human words. I'm not going to use random numbers, because nobody uses random numbers. 80% of most people's passwords are going to be some human word, usually the name of their cat or their significant other or a kid or whatever. Add 1 or 2 or 3 numbers on the end of that, and then sometimes put an exclamation point or a question mark on the end, and I can get most people's just by doing that. So what we do is we create what's known as a dictionary attack. A dictionary attack starts with a dictionary table. A dictionary table is just a huge text file that has a lot of human words in it. That's it. Hundreds of millions of human-y sounding words that people have learned over the years are commonly used as passwords. These are absolutely free tables. You can download them. They're massive. You better have many, many terabytes of space available. But it's just a list of human-sounding words. And it's going to have things like Mike1, Mike12, Mike123, capital M, lowercase I-K-E, 123. You get the idea? Gazillions of these are in a dictionary. So we can go ahead and do a dictionary attack. Now keep in mind, what we're doing is we check something and we hash it and we compare it to a hash. And if it matches, we've got the password. So what we could do to speed things up is we could take that dictionary table and go ahead and add, you guys ready? We'll go ahead and pre-hash all of these values. So not only do I have the letter A there, but then I'm going to have the hash of letter A. Not only do I have AA there, but I'm going to have the hash of AA. Now all of a sudden, this dictionary table isn't just a list of human-sounding names, it's a list of human-sounding names and a list of passwords. Now if you want to do this, go ahead, people have tried it. It's going to be like petabytes big. It's massive. So, but it would work a lot faster because we don't have to actually go through the hash calculation. They're already pre-made. So what we do instead is we use a special type of table called a rainbow table. A rainbow table is still a table that has passwords and hashes, but it uses some very advanced math called reduction functions to make it a lot easier to search. So in essence, what it does is it searches on the hash values as opposed to simply on the passwords, and it speeds things up dramatically. And no, I do not understand the math myself, but it works. The important thing is that we can now make tables that have dictionary words and the associated hashes, but instead of being petabytes big, it might just be a few hundred megabytes. It's groovy math that allows us to do stuff like that. So if I want to hack a password, 9 times out of 10, what I'm going to do is I'm going to boot onto a system using like a bootable diskette or something, and different operating systems have different places where they store the usernames and passwords. This is all well documented. Just Google it. And I'll go out and I will grab that list of usernames and password hashes. Once I've got that, then I'm going to do what's called an offline attack. I'm just going to go ahead and copy that, shut that computer down. I'm done with it. And I'm going to run over to my attack system with my 30 or 40 usernames and passwords in there. And I'm going to start setting tools with names like Cain and Abel and looking at all these pre-made rainbow tables that I've got set up. And I'm going to run that thing. Now look, if I've got 30 passwords in there, maybe I only get 5. Maybe I only get 1. Who cares? I only need 1 and I'm in that system. So that works out really well. But the problem is we don't want people to attack our systems. So what we'd like to do is we like to come up with ways to make it a lot harder for things like rainbow tables to work. So one of the things we do is called salting. Salting is a random value, okay? And this random value, and it's not secret. Anybody can see the salt. But let's go through a situation. Let's say, for example, here I've got a password, and instead of just hashing this password, I'm going to add this arbitrary string of value. This is the salt. I'm going to add that to it, and then I'm going to go ahead and hash that. Get the idea? By doing this, even if the bad guy knows what the salt value is, he doesn't have a rainbow table to attack that. So he would have to be doing it one at a time, or he's going to have to regenerate a rainbow table. So salting definitely helps things, especially as it gets longer and longer. So I can take the password, I can add the salt, and I can go ahead and hash that. Or I can take the password, hash that, then I can take that value, add the salt to it, and then hash that. It doesn't really matter. What I'm doing is I'm defeating rainbow tables. This is not going to defeat brute force, folks. With brute force, we could, it's just going to try every possible valuation. But keep in mind, most of these hashes are what we call SHA-256, which is a massive, massive hash value and extremely difficult to do brute force, unless people are lucky. Now, the other thing we can do is called key stretching. Key stretching has some similarity to salting, but it goes, I would say, a step further. Like, for example, with a wireless network, anytime you have, like you're using WPA encryption, you have to set a password, a shared key for anybody who wants to get on the SSID. And anybody who wants to get on that wireless network, they got to type that code in. We've all done this. But built into 802.11 is called a key stretching function. It's called Password-Based Key Derivation Function 2, PBKDF2. And really all it does is it takes whatever key you've typed in, let's say you just use the word Timmy, so it puts in Timmy, and then it might add the SSID, and then it might go ahead and hash that like 4,096 times. So it has a similar feature to salting, but it tends to be a bit more complicated. And we see it in stuff like wireless networks where it's very, very common to do. So for the exam, make sure you're comfortable with the concept of brute force versus dictionary versus rainbow tables. And remember that we protect all of our passwords and keys via salting and key stretching.